Okay. All right, so continuing on a similar theme. Okay, this should say, I think, 2002, not 1992. Maybe Robin Kaiser was there. I don't know if anyone else was. This was a book, a set of lecture notes produced from a Les Houches winter school or Easter school or something like this. And so I'm trying to match both parts of the conference by going from classical to quantum, so that this will all come up. But back in 2002, here you have exactly this HMF model that we just heard about, and some particular dynamics, and you get these structures forming. This is a quasi-stationary state. This is purely classical. I'll show this picture again in more detail, but this is classical particles interacting, each of them through a cosine potential. And so in a nutshell, what I've done is done the quantum version of it. Now, unfortunately, here time is running down, and here time is running up. But I didn't want to twist my pick. Anyway, I should have done. So this is the quantum version, and we'll get more into that. But of course, you can see that there's an interference pattern. And then also, a little more recently, we've looked at solitons in this model, which speaks to the question of integrability in these long-range systems. Okay. So, all right. So this work was primarily done by my graduate student, Ryan. Here he is. And where we work at McMaster University is in Hamilton right here. And it's about an hour to Toronto and about an hour to Niagara Falls. And this is New York, and there's New York City somewhere over down here. Okay, so you're welcome to come if you're ever in the Great Lakes area. All right, so what I'm going to talk about, again, is thanks to Lapo for introducing very fully, actually. So I'll be able to wave my hands a bit more. I'm going to talk about collisionless relaxation and a sort of hand-waving explanation. And then I'm going to talk about, in particular, violent relaxation in this quantum version of the Hamiltonian Mean-Field model. And finally, into caustics. And this work is... one of these is written up, and the other one is on the archive. All right, so we heard this before, so let me give my explanation of it. So this is this relaxation time. So I got this from this is a sort of classic textbook in galactic dynamics. If you have a particle traversing a galaxy, so the particles in astrophysics would be stars, and they're traversing a galaxy, which would give a crossing time. Then the relaxation time through two-body collisions depends on n, and so diverges in the thermodynamic limit. So the system never comes to relaxation in the sense of Boltzmann. And as Lapo said, it's basically irrelevant on a lot of, it can be longer than the age of the universe. And the way I like to understand this is it arises from the cumulative effect of many two-body encounters. Okay, it's not contact interaction. I mean, nothing is. Interactions are always mediated by fields, or electromagnetic field usually on our scales. But nevertheless, you get these two-body interactions, each mediated by a 1/r² potential. And it's the discreteness of matter which leads to a diffusion of the momentum. And eventually an erasure of memory and initial conditions if you could fulfill this time. And so you get proper relaxation. But for any time less than this, the system doesn't relax in the usual thermodynamic sense. But you still get something called collisionless relaxation, which is this violent relaxation. But essentially what you can understand is that the system is now, this particle doesn't distinguish individual point masses, the granularity of the galaxy. It just sees this smooth macroscopic mean field potential from the sum of all, but a smooth one from all the particles. Okay, and this has been also looked at in more sort of down-to-earth systems, StatMech systems, by these authors here. Okay, so so if your time scale is less than this Chandrasekhar time, or the two-body collision time, then you get something called collisionless relaxation, and the most basic version of this is phase mixing. So if you have a bunch of pendula, which are independent, and you put them in phase space, and you let them occupy some little region of phase space, some range of angular momenta and angles, and you let them go, then because of the nonlinearity of the cosine here, of this pendulum, when it starts executing big angles, you find that the inner ones go faster than the outer ones. Okay, so you find that this initial distribution gets smeared over phase space. Okay, but so the period depends on the energy because of the nonlinearity of the system. And it's described by this collisionless Boltzmann equation or Vlasov equation. Okay, but Louisville's theorem says that when you have this kind of Hamiltonian dynamics in phase space, that your density of phase points should be constant, so you don't get any true relaxation. But what one can do is this coarse graining idea that Lapo mentioned, which is that originally due to Lynden-Bell, where you coarse grain. And when you coarse grain, you smear over the gaps between these, you get these finer and finer filaments, but when you coarse grain, you smear over the gaps and you lower the density of phase points, you increase the entropy. And so the system then relaxes in that sense. And so you can, under those constraints, you can find sort of equilibrium systems. It's called Lynden-Bell statistics. But what I said on the previous slide, these were independent pendula, so they were not exchanging energy amongst themselves. Okay? What happens if you can exchange energy between the pendula? Well, then you have this kind of situation. So imagine a particle rolling around in some potential. If the potential is constant, okay, so it's got its kinetic energy and then this giant sort of mean-field potential, if the potential is constant, then the energy of the particle is going to be constant. But now, if this is changing with time, if phi is changing with time, let's say as a star collapsed or a galaxy collapses, then you can either suck out or energy from the system, or energy can be delivered to you. And so this is essentially Landau damping, where a particle surfs this wave, and Landau damping cases where it extracts energy from the wave, and you heat the particle. So what Lynden-Bell showed is, so that this is what's behind violent relaxation, is where this potential here is time dependent. And he showed that indeed it doesn't depend on the number of particles here. So it's quite different from this Chandrasekhar relaxation, the true thermalization. And it just depends basically on the time scale. This time scale is the time over which this potential changes by its own value, basically. And it's independent of n. Okay, so that's violent relaxation, where you need some time-dependent potential. All right, so once again, you've heard this already, so I can go somewhat quickly over this. The Hamiltonian Mean-Field model, we can either think of it as a bunch of rotors now, which are interacting using an XY coupling that just depends on their difference in their angle, or exactly equivalently, it's particles on a ring. Okay. And so their interactions depend on the cosine of either their two positions around the ring, the difference between their two positions, or their difference in their angles. And you can have the case of attractive interactions, at least at short ranges, where epsilon is less than 0, and that's the sort of ferromagnetic case where the rotors would like to line up, or the antiferromagnetic case where epsilon is greater than 0. And so you can define as an order parameter, so there's a phase transition in this model, and you can define a magnetization, just averaging over all their positions. If this is the magnetization around a particular angle you choose, could be just 0, say vertical, and you sum up all of these cosines, and you get this magnetization, which tells you if they're lined up or not. So this is an absolutely classic model for those that haven't heard of it, and here is an incredibly small subset of the total number of papers on it. So I'm sorry if your name's not there and you've written many papers on this. All right, and it can be realized in cold atom systems. So this is a picture of, where's Tobias? Where is he? There he is. So did you know you were realizing the HMF model in some form? You probably did. Giovanna probably. Well, is she coming, actually, Giovanna? I was hoping she might be here, but she's not here yet. No. Okay, I made those efforts to put her name all over it. I thought she'd like that, but no. Okay. All right. Well, okay, so Giovanna Morigi is a theorist who's worked a lot on implementing this model in cold atom systems, particularly in cavities, and we have a sort of one of the world experts in the experiments of these things, where essentially where you have, wrong way, where you have these long-range interactions which are mediated by the cavity modes, which are basically cosines, these standing wave modes, the electromagnetic field modes inside the cavity, can be essentially infinite range, and they take this cosine form. And in a standing wave cavity, you can almost realize the Hamiltonian Mean-Field model. You also get, on top of this difference between x and x prime, the positions of the two atoms, you also get one which is the sum. But there's other ways of realizing it, either by going to higher dimensions, or I claim in a ring cavity, you can get rid of the sum term and you really get the HMF model. And of course, these systems are very cold, so I should have said these are very cold atoms. Does the word cold appear in that? Quantum gas, there you go. So you can look at the quantum, potentially the quantum behavior of these things. Okay, so back to then violent relaxation, but in this specific HMF model, what does it look like? Well, it depends on what your initial conditions are. That's what we heard from Lapo. But let's consider a particular initial condition. We think of the particles on a ring. Take that picture. And they're almost perfectly distributed. In fact, that they could even be perfectly distributed, uniformly distributed around the ring. Okay, and that's what's shown. I hope you can see it, but a sort of the uniform yellow color at the top. But you introduce some slight perturbations in their velocities. Or you could have it that you just introduce some slight perturbations. The distances between them are not perfectly equal. You get the same result. And then you let the system go. Well, then an amazing thing happens. So this is for the repulsive case. So the repulsive case, the thermodynamic ground state in the Boltzmann sense would be the particles equally spaced around the ring. So you're incredibly close to equilibrium. And yet when you let the system go, you find that there's this dramatic collapse to 2 points around the ring. So it breaks its symmetry, and the particles like to aggregate around 2 points around the ring. So this is around the ring, this is the angle around the ring. And then they break up into these nice cusp shapes, and then they reform, and this goes on and on and on and on. You produce a halo of slightly higher energy particles which take away the entropy, but what you find is most of the particles eventually, after very, very long times, will settle at 2 points around the ring, which is completely different from the thermodynamic ground state. And then eventually two-body collisions will take you back to the place you very nearly started at, which was the uniform distribution. So it's very surprising to see this kind of behavior. You start near equilibrium, and then it drives you completely away from equilibrium. So I think I've said all this. So as time, these cusps, or chevrons as they were called in some of the original work, they become narrower with time, and the system is trapped in one of these quasi-stationary states, okay, which is not the same as Boltzmann equilibrium. All right, so that's, and you can ask, there was a question about attractive versus repulsive interactions. Well, so in the attractive case, you get something strongly analogous to a gene's instability, or a star collapses and the system sort of collapses. It's rather intuitive what it's going to do in that case. It's much less intuitive what it does in the repulsive case, where you get that bicluster I showed on the previous slide. And there's a very clever calculation by Julien Barré and colleagues, where they show that dynamically, when you integrate out the fast oscillations at the plasma frequency, so it turns out there's a fast frequency and a slow frequency. Maybe you can see the little oscillations at the fast frequency. When you integrate out the fast degrees of freedom, you get an effective potential for the slower degrees of freedom, which has twice the periodicity, and so you get like a double well potential, and that's why it likes to sit in these two wells. But this is a sort of dynamical effect, a very cool one. Okay. But one last thing. Notice the difference in time scales here. There's a factor of like 50 in the difference between these. So this happens really quickly. This is very slow. All right, and why is it forming cusps? Well, basically because of these pendula, they're turning at different rates depending on their initial angles, and so you get this twisting in phase space, which when you project it down onto, let's say, one of the planes, angle versus time, you get this. You see these fold lines here that form this nice cusp distribution. Okay, actually, so if anyone here knows me, I absolutely love singularities and cusps, and I always love to point this out. So who's seen this in their coffee cup? Anyone? A few of you, I hope. So this is an example of a cusp formed in light. This is just a caustic light bouncing off the back wall of this cup, but it's also a very generic phenomena that you get these kind of singularities, these cusps. There's more complicated forms on the bottom of swimming pools. Rainbows are also example. This is gravitational lensing, ship waves, rogue waves. These are all examples of focusing of waves in nature, natural focusing. And in particular, this cusp shape comes from the caustic, from where the rays are piling up along this envelope of the family of rays. And if you're Italian and you like to stare into your coffee cup a lot, which I guess is what Leonardo da Vinci was doing, you realize you understood these back in 1508. Okay, but the one point is that this is a singularity. Okay, if you solve the ray theory here and you ask what is the intensity along this point, then it's actually singular. Formally, it's infinity. And I spend my life worrying about infinities. Well, it turns out that there's only certain structurally stable singularities around, and they're categorized by something called catastrophe theory. In one dimension, it's just a point, but in two dimensions, it's exactly this cusp shape. So structurally stable singularities are singularities that resist perturbation. So for instance, if this coffee cup, if it was a plastic cup, and I pressed in on the back wall, this structure has integrity. It would be qualitatively the same. Quantitatively, it would change. It could get sheared and stretched, but it has structural stability, so it wouldn't just completely disappear. Whereas a focus point, if this was a parabolic mirror, a focus point is unstable and explodes exactly into this cusp-like shape. So that's another reason why we get these cusps in this system. And these things are described, the mathematical description, by these actions. So this is actually an action, and depends on, in the case of the cusp, these two control parameters, C1 and C2, and they describe locally, the action locally to this singularity. And so another madman, Dali, got very interested in this. He believed the biggest singularity was in Perpignan, so the French people, and it stretched all across Spain, apparently. More precisely, Perpignan railway station. I don't know why, but okay. So you can get the local wave function. So we want to quantize these things, and you can get the local wave function by, of course, exponentiating the action and then integrating over all the paths. So you can think of this as a path integral. The simplest case, you get the area function in this. For the cusp case, the two-dimensional case, where you have these two control parameters, you get something called the Pearcey function. And here it is. So you get these nice curved, here's the classical caustic, but now it's dressed by, that's where I was talking about, these curved things. Different story. But you get this interference phenomena which removes the singularity. And if you look at the phase, it's even more interesting because you get pairs of vortex-anti-vortex pairs. But that's, again, a different story. So we expect this to dress, this nice shape here, to dress all of these cusps, these universal wave interference patterns. Okay, so let's go to the quantum model then. And so what I'm going to do, so that the Hamiltonian Mean-Field model, despite the fact in its name it says mean field, it isn't, in the many-body sense, a mean-field theory. Not yet. I'm making it one in this slide, but in fact it's a many-particle theory. It just behaves very collectively because of the long-range interactions. But now I'm really going to make it a mean-field theory by assuming that my particles are, for instance, Bose condensed. So they all share exactly the same quantum state. We'll call psi here. Okay? Then we can describe the system by a single nonlinear wave equation, which is like the Gross-Patevsky equation. If this was the Gross-Patevsky equation, I would have here mod psi squared, a local nonlinearity. But in this long-range model, we have a non-local nonlinearity given by this mean-field potential, and it's just a Hartree potential. So it's summing up all of these cosines between all the different points. And there's a remarkable thing, which if I don't overrun like everyone else, I might prove to you at the end. It's very simple. It's a two-liner, but is that you can this sum of all these cosines in this model actually reduces to a single coherent cosine. So the whole system is interacting through a single cosine. It can move its minimum around the ring, but nevertheless it's a single cosine, and it has an amplitude which is exactly this magnetization I was talking about, of which says whether the particles are clustered or not. Okay, so we can think of this giant cosine, and its amplitude can change in time during this violent relaxation. Okay, there's a hydrodynamic formulation of this just by doing the Madelung transformation, and you get your quantum Euler equations, which look exactly like the classical Euler equations, except they have an extra contribution on the end, which comes from the quantum pressure. And that's going to be significant. It's going to change. That's going to be the key player in changing the violent relaxation quite a lot. I'll also say, and I haven't written this in a paper, but the coarse graining, a question I have to the audience is there's automatic coarse graining in quantum mechanics, which comes from the discretization of phase space into units of h bar. That might be too simplistic a picture, or it might not, but I'd be very interested to speak to people about that. Okay, so we have this quantum pressure term, and there's one key parameter, which is basically the ratio of the kinetic energy to the potential energy. It also plays the role of an effective Planck's constant that appears in these equations. Here you go, you see it. If it goes to 0, then our quantum pressure term goes to 0. All right, so what happens then when we solve this numerically, this generalized Gross-Pitevsky equation? Well, we get this. So this is times 0, and then times going up this axis. So initially, nothing happens. We start off with a uniform distribution, almost perfectly uniform, just a very slight perturbation as you go around the ring. Okay, but then you find that the system spontaneously, like in the classical case, forms these caustics, these cusps, except now they're regulated. There's no infinities. I can sleep again at night. Now I've got rid of the singularity, and you get this beautiful interference pattern, this Pearcey interference pattern, which does introduce new length scales into the problem, but time is short, so I haven't gone into that aspect of it. You can understand if you look at, so this is the full nonlinear theory. If you do the Bogoliubov theory to this Gross-Pitevsky equation, you find that your excitation spectrum looks like this, and you get two contributions. One is the classical plasma oscillations, which occur because the cosine has these two terms, these plus and minus k terms. And then there's also a purely quantum part that depends on chi squared, on like h bar squared, and those behave like free modes. So you can describe the early formation of this through the instabilities of this system, through the gene's instability when this is minus, for example. Okay, how about in the repulsive case? When the repulsive case, things are more interesting because you get this bicluster. So here's a bunch of pictures. On the top row, I'm taking them from quantum to classical as I go from left to right. So as you start off very quantum, basically nothing happens with time. We put in a very small perturbation, but it's unable to evolve because the quantum pressure overcomes this sort of modulation. And nothing, so we suppress violent relaxation, basically. And only when we become more and more classical do we begin to reproduce something that looks like this bicluster. But it's still a very different scale from the classical. The time scale at which it occurs is very different from the classical case. Meanwhile, we can overcome the quantum pressure somewhat by increasing the perturbation. And in this line here, we're increasing the initial perturbation, so that's the magnitude of the initial plasma oscillations. And we find that eventually we're able to overcome the quantum pressure in the sense that we trigger the instability, and we get these biclusters now eventually appearing. But we need this larger. It's still perfectly well. It's still well behaved in the sense there's no singularities. It's all smoothed out by interference effects, but it takes we had to overcome this initial resistance due to the quantum pressure. Okay, and that allows us to write this. To come up with a sort of dynamical phase diagram. Okay, so it's not a ground state phase diagram because that doesn't really exist with these long-range interactions. But we can write down a dynamical one. And so the idea, so it's again these two axes. So we have chi. Unfortunately, again, I've reversed my axes. So chi is going from quantum to classical here, and this is the size of our perturbation. So if we were in the purely classical Hamiltonian mean-field model, we'd sit at chi equals 0. Okay, we wouldn't have this degree of freedom here, and we'd have two options. We'd have plasma oscillations the plasma oscillations would never kick off into this bicluster if we have very, very small initial excitations, but once they get above a certain threshold, then you get the bicluster. However, once you add the quantum axis, what you find is as long as the quantum pressure is larger than these initial fluctuations, then you just remain in the plasma mode, and you never really take off into the bicluster. And then finally, these free Schrödinger modes, which in that Bogolubov relation I showed, these were the purely quantum terms, these guys begin to dominate and really suppress violent relaxation. So the message is that violent relaxation is basically suppressed by this quantum pressure, and I would very tentatively wonder whether that's because the coarse graining in the deep quantum limit means you're already at some sort of equilibrium situation. You're already in a high entropy state, so to speak, even though it's a mean field pure state. Okay, in 2 minutes then, solitons. So it turns out that there's an exact solution for these equations. I promised you I'd explain why the density can be written, why this potential can actually be written as a giant. This is, the sum of many cosines, but it can be written as a single giant one. Well, we know this lives on a ring. It must be periodic. Let's Fourier analyze it. But then you notice that because we're integrating to get this potential, we're integrating, multiplying by cos and integrating, that picks out just the plus and minus 1 terms in this. So those are the only important ones. Let's give them an amplitude and a phase. And then we find that our giant mean field potential exactly takes this form of a large amplitude and a single cosine. So then what we get when we put this into our equation here is exactly the Mathieu equation describing a single quantum particle in a periodic potential with one slight difference, an important difference, and that is the depth of this cosine potential is set by the solution itself. Okay, so this is m, the magnetization here, which is the magnitude of this part here. So you need to solve this equation self-consistently so that the wave function matches its own potential depth. But that can be done numerically. And what you find is something that looks like this. So we can map it, as I said, onto the Mathieu equation, and the sort of in the mathematical terminology for the depth of the potential is Q. So that's what I've plotted here, Q versus this reduced sort of Planck's constant here. What you find is when chi is quite large, we're very quantum, we get no solutions, and then at a critical point, the first solution appears. This is, for instance, this guy is at 0.5, then you get 2 of them. You get this solution and this solution. And so this is what we normally think of as a soliton with no nodes, but you also get another solution here. And as you keep going, you get more and more solutions appear. Okay, so as you make the system more and more quantum, and they get more and more localized. That's why I'm calling them solitons. I had a big argument with a mathematician colleague of mine saying, oh, they can't be solitons, but I claim they are. And the referees agree with me, so that's good. And so basically, as you go more and more classical here, they become more and more squeezed. But what's unusual about these solitons is that in comparison to the normal local Gross-Patevsky equation, where you have a contact interaction, where you only have one bright soliton, and you don't get these higher modes. Here you get a whole tower of these solutions. Okay, and I will skip this, but there's a phase transition in this model, which comes out of this exact solution. Okay, so what have I told you? I've told you that violent relaxation persists still in the semi-classical regime. It's nicely regulated by interference. So you don't get these singularities in these cusps. But in the deep quantum regime, it can be suppressed entirely by zero-point motion. And this is my tentative question to the audience. Can this be viewed as a sort of as quantum coarse graining, the fact that you kill off violent relaxation before it even got started in the deep quantum regime? And you can find exact solutions to this very simple model, and they become highly localized. There's a regime in which they're highly localized, and you can consider them as solitons. And the fact that although the original Hamiltonian Mean-Field model is not thought to be integrable, the mean-field model that we have is, and that's why it gives these exact solutions. Okay, thank you for your attention.
Thank you very much. Questions, please?
Dark matter?
not yet, but